Hey there, everyone. My name is Ryan Schul. Welcome to my data science channel. I talk all about different data science techniques and methodologies, and I include topics like artificial intelligence, deep learning, machine learning, optimization, and things such as this. So today's topic is a little bit more leaning towards optimization, I would say, and we touch on a bunch of different topics. So let me take you through it. Today, I want to talk about managing urban traffic flows. We're going to use Python. Of course, I use Python for all of my demos and all of my videos I post here. So today I want to focus on a smaller city just outside of Denver. It's called Boulder, Colorado. I've been there a couple of times. Absolutely beautiful, gorgeous, love it. I want to be there. I want to be living there. I actually live in New York City for a couple of reasons, but if my circumstances change soon, I might actually be relocating to Boulder, Colorado. I love it that much. So I'm going to focus on that because I love the area, I love the town, fantastic. And also, it's a smaller city, so it's a little bit easier to analyze um, this type of environment. Much easier than a mid-sized city like what, for instance, maybe Tampa, um, Phoenix, San Francisco would probably fall into that category, and much easier than analyzing traffic flows in a large city like New York City. That's where I live, right? But New York City is very complex. It's a beast. It's a behemoth. Okay, are you really going to understand all the nuances of traffic flows around New York City? Probably not. But I mean, we can work our way up there. Maybe in the future, I'll do a video about that. But I think we're just going to start small, make this bite-sized and consumable, right? So we're gonna focus on a smaller town. Boulder, Colorado, I think is an excellent choice. So why would we even want to understand how to manage traffic flows? There's a variety of reasons, right? Analyzing and predicting urban traffic flow is critical for optimizing city mobility, people getting around point A to point B, commuting, and preventing big, nasty, ugly traffic jams, right? Reducing traffic congestion, improving public transportation and the efficiency around that, encouraging people to commute together, right, to carpool, um, incentivizing people to take a bike or to walk if that's an option, things like that. So there's a variety of different things we're going to look at too, and the overall sustainability of urban planning, right, including ride sharing, smart city development, smart city development and growth. I made a couple videos about that. Also about Boulder, Colorado. I like it a lot. So check out those other videos if you have a chance. And basically that's it. So let's get into it. We will need a Google API key to be able to run this first. To be able to run this first cell of code in Jupyter notebooks. These are called cells. So basically, I will show you how to get the key right here. If you go down here at the end of this, notebook, I have a link to getting a Google Maps API key. So if you go over here, you can copy and paste it, put that in here, or just Google for it, right? Manage APIs, and it should be, let's see, API keys. I think this is it over here. API keys, principal. There should be a way to log in. Where is this thing here? Authentication, documentation, Google Cloud. Register for next. No, sorry. Oh, console. Okay. Sometimes they change these things. You have to click around. I just did this a couple days ago. I guess it changed overnight. Okay. Okay. So, anyways, just look for the console, and then you have your API keys and services over here, and you can see these are all my API keys. Some are turned on, some are not enabled, some are enabled. But then you have a couple controls over here like this, right? And you have your credentials tab over here. So I would encourage you just to go ahead and get your own key. It's going to look something like that. You can copy and paste it. You have your creation date. Desktop is the type of key, and then if you want to change it or whatever. So you have your keys over there. That's the first thing you're going to have to do. And obviously, like, these keys are confidential and personal, so I can't share mine with you for obvious reasons, right? It's like the key to everything in your cloud environment, right? So you have to get your own, but it's free, it's easy, very straightforward and very simple to do that. So very streamlined process. Go ahead and get the key. You pop that in here. Once you pop that in here, you can run all the code. Okay, so I'm going to give you all this code You can copy and paste it. You can download code. When I post a video, I'll share the code with you. Download, copy, paste it into your own environment and run it, and it's going to work fine. All you need is this key right here. When you generate it, and it's totally free, you'll have everything you need. Copy, paste it in there, and run this. So you can see I have an origin and destination, right? So I'm saying the origin is Boulder, Colorado. The destination is Denver. So um, just um, just humor me for a minute. We're going to get into Boulder in just a minute. But the first thing I want to showcase is just how to get directions and how this API endpoint works a little bit, because the Google Maps API does all kinds of wonderful things for you. There's a Maps API, there's a Places, which is pretty cool too, and they'll have all kinds of information about restaurants, museums, anything you want to look on Google Maps. It's all contained in that Places API, and the Google Maps will give you the directions. I'm pretty sure you guys have this on your phone already, right? So we're going to have the origin and the destination. This is the URL, pretty standard URL. You have the origin over here. If you copy and paste, you can see basically how the URL works, right? So here's the origin, all right, and you put that in here. Here's the destination. If I copy paste that over here, you'll see where that goes, okay? Destination is right there. And then the API key goes right at the end, right? And there's the API, and that matches that. So you can see how you have these three things. You concatenate them all together. You create the URL. You send that URL to the Google Maps API endpoint, and that will generate a response. You fetch your response. Okay, you fetch it. It comes back as a JSON string, and then you unpack that JSON string, and you'll have everything you need based on the requests. Okay, so you have the root colors here. This is just a couple little things that I put together. Basically, everything is contained in here. You have to kind of pretty, make it pretty, make it beautiful, make it more human readable. Prettify, I think, is the word. So you get your response in the JSON string, which is a little bit ugly to look at, but once you prettify it, or let's call it embellishment, once you embellish the response, then it becomes more human readable and more intelligent, I guess. So that's a good word there. So you have the response from the API, you have the origin and the destination, and let's go down and see what this thing looks like. And again, I'm not going to run this in real time, right? Because I can't share my API key with you guys, but generate your own, pop it in there, and you will get this right here. Just change the origin and destination to be whatever you want. Okay, and then basically the request will create a couple different routes for you. I think it creates a maximum of 4, but it'll create at least 1, obviously, and 2, and I think 3, and depending on the distance that you're driving between the origin and destination, you get up to 4. Okay, and I think that's a max. That's the max there. But if you think about it, there's so many different ways to get from point A to point B, right? And Google is pretty flexible and pretty generous with the way that it delivers data to you. But if there's maybe, I'm thinking if you drive between New York City and Boston, there's probably at least 100 different ways to go, right? It is probably the most efficient way. That's what Google is going to recommend. There's an alternate way if you don't want to deal with a lot of traffic. It might be less traffic. It might take longer mileage-wise, but it might actually be faster, right? So Google could recommend those two, the shortest distance, the least time distance. You can pick a scenic route. You can pick a route with no tolls, right? There's multiple ways to get from point A to point B. And then, of course, there's all kinds of out-of-the-way routes you can take. And you can, if you're going from Boston to New York or vice versa, you can go through New Hampshire. You can go through Maine. That definitely is not the most optimal route, but that's another way to do it, right? So it's probably hundreds of ways. Google is going to limit you to 4 maximum, right? And it's typically what I said, like the shortest distance, the fastest, the most scenic, and then the route with no tolls, right? So here's route 1, and it printed out all the directions. So that's pretty nice. Okay, and this is route number 2, again, with all the directions right there. And typically you would have this on your phone, and it's updating as you drive, right? Everybody's seen this thing, so it's pretty cool. That's a great invention. That's my favorite inventions, by the way. So that's how it works behind the scenes, right? This is Python code to go ahead and make a request to the API endpoint, pull back the data, and then start to unpack it. And you can see right here, Google is giving us 2 routes, right? From Boulder to Denver, and we can zoom in, we can see the details. So this one kind of looks like a highway. We're getting on the exit ramp or an entrance ramp. And this one over here is going like more of a back road kind of approach to that, right? So that's the first thing I wanted to show you, just basically how Google Maps prepares and handles this data, right? So let's scroll down to the next cell here. Now with the API key, now I'm just using API key again and again. I'm using it over and over. So I guess it's five times right here. Oh, 9 times. This is number 5 of 9, right? So you put in your API key and then you'll have access to everything else. I'm just using it once. And then every time I need the API key, I'm just referencing the original API key, right? So this is just to demo how everything works here. And you might not even need all of these cells that I'm giving you, but you know, to really set up this this learning point here and to execute, this is how you do it, right? So input a number of routes to analyze, so we can input the number of routes, and this is going to give us actual real-time directions and traffic congestion, right? So I'm sure you've seen this on Google Maps. Red is slow, there's a lot of traffic, a lot of congestion. Orange means there's a little bit of traffic, not too bad. Cars are moving a little bit slower, right? So it's kind of orange is kind of like a warning sign, and everything that's green is good, right? Green is go, green is good. In the stock market, green is up, stocks are up. So I think green is synonymous with good or go, and red is synonymous with bad. In the stock market, if your stocks are down, it's going to be red. And if you're in Google Maps, red means warning, there's a lot of traffic. Okay, so we got the first real-time traffic map, which looks pretty cool. So we're going from Boulder to Denver. The first map just gave us directions spelled out here. All the directions are labeled right there. And in the second map, we actually get the concentration of traffic. And is it green? So mostly, in this case, it is mostly green, right? So green is go, green is good. And there's a little bit of orange, and it's actually on the path that we're taking, and it's fine. It is what it is, right? So traffic is going to be a little bit slower. There's nothing that we can really do about that, okay? But we're going to see there's a couple things that we can try as a resident of this town in Boulder, right? Let's pretend that we live in Boulder today. That'll be great. Not reality for me yet, but sometime soon, hopefully. So any government official, if you're working in a traffic area, police, traffic, what else? Any of these people I think would be highly interested in this kind of technique, because I'm going to try to predict traffic flows and then manage how this traffic flows in the town of Boulder. But of course, this can be applied to any town, right? So the ideal scenario would be to get this data in real time for your city, for your county, for whatever area you live in. If you're a government official, or a city planner, or city police, something like that, right? I think it's all relevant for these types of people, and for myself too. I think this is interesting to look at this and study this stuff too. Okay, so how can we predict and manage traffic flows in and around Boulder? But again, it could be any city in the United States, any city where Google Maps will capture the data. And by the way, Google Maps has all this traffic flow data. You can see it right here. They have detailed data about sensors in high congested areas, even in lower traffic areas. They'll have like the number of cars that pass through every minute, signals for red lights, green lights, orange lights, things like that. They'll collect all this data, right? So it's pretty interesting. So when we get this information, we can be able to, we should be able to do traffic flow prediction using historical Google Maps time series forecasting, right? And this is exactly what this is. This is real-time directions and real-time traffic information going from Boulder into Denver, Colorado, right? So we have all that. We can go ahead and do reinforcement learning. This is abbreviated RL for traffic optimization, and try to optimize traffic signals. I'll show you that in just a minute, how to optimize green lights and red lights, and how to switch back and forth between the two based on how congested the traffic area is, right? So I'm going to show you how to do that in just a minute. And this can reduce congestion, traffic, transportation prioritization, right? And all of these can become policy effects. So all of this can be legislated, this can be enacted, this can be changed to make the city much more efficient, right? And much smarter. So we will go ahead and collect in the next demonstration here of how to manage traffic flows. I'm going to go ahead and collect information about more Google Maps data here. So I have the API key. You saw that over here. It's using that initially, right? And it comes from over here. Copy, create your own, and then copy and paste it. You can use it there to get the map, to get the directions, to get the traffic, congestion. And the next step here is to get historical actual travel times between these two places, right? So I'm looking at Boulder, Colorado and Denver, Colorado. Okay, and how long does it take to get there over the course of time with actual minutes? Now, this is based on historical data that I pulled from Google Maps. And these were the travel times that it took cars. And they capture all this from your phone, right? Like Google knows, okay, this guy or this girl is going from Boulder to Denver. They know the route that you're going. They know how long it takes. They know the traffic conditions. They even know the weather conditions. They know the time of the day of the week, things like this, right? So all of that is captured and preserved inside of Google's BigQuery, it's called. So that is a massive database that Google stores and maintains all kinds of useful information about Google Maps and about other Google things, right? Like all this is warehouse in their Google BigQuery database. So you have the day of the week, the year, the time that this person is traveling. This is all historical information captured and preserved, right? And they'll probably take averages. They'll probably take like, I don't even know. I never worked at Google, and I don't even think I know anybody that works at Google, but they'll probably take like a mean or an average of a bunch of different people commuting. And if it's just one, then the average is just one, right? If it's two or three, they'll take the average of those people. And if it's 100, they'll probably just take the average. Usually everything in the analytics world, and it can get pretty complicated too, but most things, honestly, are just averages, counts, or sums. Those are the three big types of analytical metrics that you'll encounter. Okay, a sum or a count or an average, and that's it. I'm sorry if you're looking for something more smart or more sophisticated. Sometimes it does get very sophisticated. Sometimes it gets very complicated, but most of the time it's just those three, right? Sum, count, and average. So we have the averages right here of all these travel times, and I am breaking this out by the day of the week and then the hour of the day. So why do we want to do this? Think about it, okay? Pretty obvious. The day of the week matters for all these commuters, right? Between Monday and Friday, so Monday, Tuesday, Wednesday, Thursday, Friday, the commute times are very pretty consistent and persistent and very predictable too. Saturday and Sunday is different, right? Because it's the weekend. So people don't have to go to work. You don't have the rush hour in the morning. You don't have the rush hour in the evening or late afternoon, depending what time you get out of work. So weekends are a little bit different than weekdays, but Monday through Friday, it's consistent and persistent. Middle of the day, overnight, these are always the same. Monday through Friday, Saturday, Sunday varies a little bit, but those are going to be the same too. So Saturday and Sunday traffic is going to be similar over the course of time. And again, these are all averages. All they're going to do is take an average, and Monday through Friday is going to be different. But again, you take averages of those. So let me go ahead and take all this information. And by the way, I just used the Google API to fetch the historical data for 10 days. If you look closely, I believe that's what I used in this example. 10, yeah, number of days is 10. So it creates a loop every hour. It goes back and fetches this data from Google's BigQuery database and pulls that back. So I have the data for 24 hours for 10 days. Okay, that's how I get 240 records here. So 24 hours times 10 is 24, right? It starts at 0. So you got 0 over here, 239. And I ran this back in time, 323. So it goes back 3 days. 3 days, and it starts there, right? So today is today's the 13th, 10/25, March 25th, March 13, sorry, that's my track of thought. March 13, 2025, right? And I'm going back to get data for 10 days over a 24-hour time period, right? So this is actual historical data from Google's BigQuery, and I went ahead and created a heat map of this. So if you look close, this is Thursday and Friday. This is what I was just describing. So Thursday and Friday, Monday, Tuesday, Wednesday are going to be kind of similar, right? And these are the times of the day. So this is overnight. This is like 2,300 hours. So it's 11 p.m. This is 10. This is 9. This is 8. So 18 is 6 p.m., 19 is 7 p.m., and 17 is 5 p.m. So 5 p.m. people are just getting out of work, just getting going. There's a little traffic buildup, kind of accelerating or maybe decelerating, right? If it's traffic, it's decelerating, but the buildup is accelerating. So we get 5, 6, 7 p.m. And you can see this pattern is pretty consistent and very persistent. So this is Thursday, Friday, Monday, Tuesday, Wednesday is over here on the right. And you can see darker color is worse. And you see exactly the same pattern in the morning, right? So here you have morning. You can tell on Friday, a lot of people work from home. Saturday and Sunday is more random. This is over the weekend and anything goes, right? Like the patterns are not the consistent commute patterns. You see people going to work. You can tell there's a lot of people that live in Boulder. They commute to Denver, right? That's exactly the story that I get from this message. And they're going in at 8, 8:30, 9, 10 o'clock. The peak is probably right around 10, actually. People are getting into work a little bit late. That's fine. No judgment here. And then they're getting out, they're putting in a decent day's work too, because they're still working 8 hours, getting in probably around 10 and leaving around 6. Okay, so that's the normal pattern, Monday through Friday. You see that. And these over here are just empty, they're just blank. I could fill them in, I could backfill, forward fill. I just didn't do that in this case. I just left those empty. But you can see the pattern repeats itself. I wanted to get over the weekend. So that's why I got 10 days. I got Saturday, Sunday, and then I have the 5 weekdays, and there's a little bit of overlap. See, Thursday, Friday. Friday is all filled in. Saturday, Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and then Sunday. It's going to cough a little bit because we're at that time I said, give me 24 hours over 10 days. So a little bit gets truncated at the beginning, at the end. But we do have that whole week captured, including the weekends. So that's pretty nice, right? So as we move on here, we can collect hourly traffic over a week. That's why I just showcased right there, right? And looking at number of days, and then total hours is number of days times 24. So we'll still see that 24, 240 pattern repeat itself. We saw that right over here. All right, 239 plus 1 for the first record right here. So 0 is really 1 in Python world. It's 0 based. In Excel, you'll see row 1, 2, 3 in databases, they count with ones, right? But in Python world and a lot of programming world, programming languages, Python included, everything is 0 based. Okay, so you see the 24-hour pattern there, and you see the same thing repeating over here. Now I'm getting, in this case, I'm not driving from Boulder to Denver. I'm just going ahead and saying, give me 10 intersections around Boulder. Give me the latitude, longitude coordinates. And I created this data, by the way. I looked in several places where I could actually get real-time traffic data around Boulder, and none of those are working. So I kept hitting the database. I kept timing out, not responsive, not giving me any kind of feedback whatsoever. Every time I made a request, it just got denied. So I had to make up the data. Guys, I'm sorry it is made up, but it is very realistic. So I wish I had the actual data in this Google data right here. I do have the actual data. So this is real Google data all across Boulder and the actual commute times. When I went to several Boulder government websites, none of them worked. I don't know what the deal is there, but basically I tried to create 10 intersections with actual GPS coordinates, and based on what I can gather from Google Maps, this should be very accurate. Now, I don't have access to some things in Google's BigQuery without paying for it, right? I don't have an account where I pay. I do have a couple subscriptions with Google, but they're all free, right? So I can't get this actual paid data, and I don't want you guys to create an account and to have to pay for that too. So I'm just using hypothetical data that, again, is very realistic in real world, but it's not the actual Google data because you have to pay for it and I have to pay for it, and I don't want to go down that path. So I created the data right here, and you can see based on the latitude, longitude, if we are in a major intersection in Boulder, the green light is going to be longer, and if it's a smaller road, like if there's a large road that passes east and west or north-south, it doesn't matter. If it's a major road that's going east and west or north-south, the green light is going to be on longer and the red light is going to be shorter. If you have an intersecting road that's smaller, just a small crossroad, those red lights are going to last longer. Okay, so major intersection, mostly green, a little bit red for the guys that have to come across the intersection, right? And there's the opposite here. So if the major intersection is north-south, those green lights are going to be on longer. If it's a smaller road going east-west, those red lights are going to be on longer. So that's the logic behind this, okay? And if you go to Google BigQuery and fetch that data, you'll see almost exactly the same thing, right? So here's the day, the hour, latitude, longitude, the congestion. Now this could be in terms of seconds, in terms of car counts, cars going through the intersection every minute, every 30 seconds. It doesn't matter. It's just a metric to just demonstrate how this data should look in reality, right? This is made up fabricated data, but in reality, it's going to look like almost exactly the same if you paid Google for it. I'm not paying, so I'm making it myself. But this is what it would look like, right? You have congestion, red light time in terms of seconds, and then the green light time. And again, if this is a major intersection, east-west, then the green light is going to be on longer. If it's a major intersection and the main road is going north and south, those green lights are going to be on longer. So here you see green lights longer here, right? And the red light is a little bit shorter, right? This one actually is the same. This one's shorter. This green light is a little bit longer. But then sometimes it's the opposite, right? Sometimes the red light is going to be shorter because you're on the side road. That's what that represents. You're on a smaller road, so you're going to have more red light time in front of you, okay? So what is the purpose of all this? Why are we trying to do this? To try to understand, can we make these lights switch faster in a more automated fashion based on congestion and traffic buildup throughout the day? Yes, that's what we're going to do in this data science experiment. So you have your traffic, it's going to come to the intersection, you have the opposing traffic coming in, and how can we optimize the whole experience for all the drivers to cut down on commute time, to cut down on fuel usage, to cut down on congestion and traffic, and just tame this beast and control it in a more efficient fashion than the way it's done right now, which is basically, as far as I know, like, I'm not a traffic engineer by any means, but if you look closely at the lights, I think there's just a mechanism that says, okay, this is going to be green for 60 seconds, and this one is going to be red for 45 seconds, or whatever the case is. This is going to be green for 25 seconds, or 30 or 45, and it's going to be red for 60 or 75 or 90 seconds, right? I think they all just go on a trigger, which is controlled by some mechanism that's just automated, but it's not smart, right? Now, again, I'm not a traffic engineer, but I would assume if you can control the pattern of the light and it's set for 60 seconds, you can feed information into that from a Google sensor or from a Google traffic API and say, okay, there's not that much traffic coming in that we need a green light. We can actually let these other guys go over here because the traffic is pretty light right now. And that is going to change based on the time of the day and the day of the week. And you know that for a fact because we have actual data that actually proves that right here, right? So the higher travel times right here are in the evening and in the morning. These are commuters going to work. We've already seen that, right? We have hard evidence, people going from Boulder to Denver. And these are the actual driving patterns right here. So for the red light example I'm making up right here, I want to replicate that, but make it much more flexible for all these drivers. So here I created an interactive animated map where you can look at the day of the week, the time of the day. You can see down here in the lower left-hand corner, kind of like the southwest quadrant, you can see the time of the day. Now it's Tuesday, 3 a.m., 5, 6, 7, 8, 9, 10 a.m., and you can see the traffic building up and is slowing down. So the circles represent the density of traffic, right? And these are the major intersections around Boulder. So as the animation plays, you can see traffic patterns accumulating and then kind of going down and then building up and going down all over again, right? So you can see the pattern throughout the day. So that is sort of like the genesis or the motivation for this whole analysis right there. So how can we make traffic, whatever you want to call it, more pleasant, less unpleasant, more manageable, less traffic, less congestion, and just better traffic flows throughout the entire city of Boulder and throughout all the cities across America and probably across the world for that matter too. So that's what we're trying to do right here. Okay. So at this point, we are going to look at 3. Originally, I thought it was going to be 4. I came up with 3 great ideas. The 4th one really didn't takeoff. And by the way, these are just 3 innovative ideas that I had. So there's a lot of things you can do with this type of analysis, right? You can come up with probably a dozen different ways to manage traffic more efficiently. Maybe there's 2 dozen different sort of improvements that we can try to make, right? This is just 3 innovative ideas that I came up with. So we're going to look at the red light time, the green light time, and the overall congestion for these 10 intersections, right? And if you look at the sample of the data, that's what we have here. So we have day, hour, latitude, longitude. Those are the lat-long coordinates for the map, right? Or the intersection, whatever, on the map. The overall density of congestion, the red light times, and then the green light times. Okay, so that's the data that we're working with. And again, this is just my hypothetical scenario, but based on actual Google data that we can collect for commute times, data that we can get from sensors in high density traffic areas. I'm sure that we can fetch the data, collect it, and analyze it, and then feed that into the signals that show red or green, and let the traffic pass or stop the traffic until this signal turns red, and then the opposing traffic can pass. I'm sure that this can be done, right? I'm 100% confident that this can be done. We have the tools, we have the technology. This is what we should be doing. This is what I'm trying to prove right here. So then we have the day, hour, lat, long coordinates, visual congestion, the red light time, green light time, and then the optimized congestion. Okay, so in most cases, this should be just about the same. Hopefully it doesn't get worse. I suppose maybe it could get worse, but that would be unlikely. But in most cases, you should see an improvement here. So the original was 34, went down to 26. Originally, 38 went down to 21. Here's 48. We got this down to 37, 36, and 36. Okay, so that one stayed the same, no improvement there. But in most cases, we reduced the congestion in that intersection. And we did that just by switching the red and green lights. So the original red light time was 30 seconds, 45, 60, and we got this, that stayed the same, 35, that went down, that went down, that went down by 10 seconds, and this one stayed the same, right? So the red light time decreased, the green light time either increased or decreased. I think in both cases they actually decreased. Yeah, so this one decreased. So actually the red light and the green light both decreased, but the overall impact was more efficient traffic flow, right? So you don't need longer green lights. And it's not always like a green light is going to be good. Sometimes the opposing traffic has to flow through too, right? So having a shorter green light can actually create less congestion, less traffic, right? So we really have to think about how we optimize these signals, right? So reduce the red light, reduce the green light, and reduce the traffic. And we have time savings over here of 7.5. Now, I'm not sure of the metric, and it doesn't even matter. This could be minutes, this could be seconds, this could be minutes per hour, this could be seconds per minute, but there is an improvement. There's an improvement here of 6.3, 10.6, improvement, no improvement, no improvement. So not every scenario is going to be improved, but if you automate the way that the red lights and green lights alternates, okay? You see what I did there? I said alternate and automate, so it sounds the same. It's actually different. If you automate the way the lights alternate, you can improve the traffic conditions. That's the takeaway here. That's the whole base of my argument, right? If you automate the way the lights alternate, you can improve traffic. Okay, so we just saw that in that case, and so I lost my train of thought here for a second. Why did that not work? Let me look into this, because all this code was working before. I think I just refreshed something, and because the Google API was turned up. No, that should work. Let me see. Let me try that. Latitude, longitude. It's complaining about this, right? Let me just look for this thing. Oh, there's a dot after this thing? Is that what it's saying? Let me see. Syntax error, right? And that goes over here. Oh, that's fine. Oh, it doesn't like that one, right? Oh no, that's inside the brackets. You know what? Let me look into this. So I have a deliverable here. Before I send out this code, before I post it on to my Google Drive, I will fix this error. I don't know what this is. This looks like it should work. I think it came from the API, because I'm not running the active API in real time right now because of the API key. I can't plug that in right now. But let me go back and fix that after this video, and I'll make sure everything works before I post the final version of code. Okay, and that one doesn't work too. Let me see if I can make that one work. That is going to minimize the red light and green light. Okay, yeah, same thing. So yeah, just like we saw before, I'll fix this other piece of code. It looks like that should work. Grouped by, it doesn't like that. But it should be able to go around that. Let me try it one more time here, okay? Because this looks fine to me. Okay, looks like it's time for a water break. This should work. Should work. Okay, just made it worse. Sorry. So let me after the video is done, I'll go back and optimize congestion. Oh, okay. I know what happened here. Let me fix this before I post the code. I'll get this working, I promise. So I showed you the red light, green light optimization, right? Let's go down here and look at this next scenario right here. So at these specific longitude and latitude coordinates, again, these are 10 intersections all around Boulder. It starts with 0, goes up to 10, right? Looks like it ends at 9, actually starts with 0. So you have 10 records here. You have the lat long coordinates, and you have the optimized red light times. So in the last example, we looked at how to minimize traffic congestion. So we saw an example of that by flipping the red lights in different sequences throughout the time of the day and the day of the week. It doesn't have to be 90 seconds. It doesn't have to be 60 seconds or 75 seconds or 30 seconds. It depends on the traffic conditions and the time of day and historical traffic patterns. We can actually optimize the traffic flow and minimize congestion, right? Just by alternating the red and green light switches right there. And these are actually the optimal times based on latitude and longitude coordinate for each intersection across Boulder, right? And I looked at 10. Originally, we looked at these 10 over here. If I go back and just show you that for 1 second, you can see how that works, okay? Over here, so these are the 10 intersections. Remember, traffic is building up and then kind of wearing down throughout the day. We saw evidence of that. These are the optimal times for the green lights and the red lights in each intersection. So you have the optimal time. And again, red light is going to be longer if that's a shorter road or a smaller road. Sorry, smaller road going east or west or north or south. Doesn't matter if the smaller road is intersection, the main road, you'll have a longer red light time. And the green light time is going to be longer if that is the main road, right? So if the main road is flowing this way, it's going to be longer. If it's flowing this way, it's going to be longer, right? So that was challenge number 1. Okay, so we did that. We took care of that. Number 2 of 3, simulating public transportation policies. We can use an agent-based model. This is abbreviated ABM to simulate the impact of carpool lanes, public transportation. Could be light rail, could be bus, something like that, or biking incentives, right? So people can be motivated to take a bike to work. We have this in New York City. A lot of employers will pay for people's city bike registration or city bike, what's it called, membership, right? So they'll pay you for that, and it cuts down on traffic all across New York City. So that's a big win. And there's many ways to do that. Like we saw carpool lanes, public transit, biking incentives. We can use agent-based simulation or agent-based modeling, cars, buses, or bikes, right? So you take your pick there and assign policies to either increase bus frequency or introduce carpool lanes or carpool incentives, things like that, right? And simulate impact on congestion. So we can test all of these ideas in real time, right? We can capture the data, we can test it, we can see what the impact is, take the best scenario and roll that out. So these are all very interesting types of exercises that we can do in real time and we can deliver today. So in part 1, you saw optimizing the way that the signals respond, right, to different traffic conditions, and all that is automated, by the way. Google has this information. The city of Boulder should have it. They should be able to implement that. If they're not, I don't know why they're not, but they should be doing that. And New York City too, I don't think they actually do that, but shame on you, New York City. You should be doing that too. This is pretty easy to implement. Not sure why you're not, but New York definitely has some issues that they're contending with right now. So that was scenario 1. This is scenario 2, and we're looking at car, bus, or bike. And then what are the motivations for each one, and then based on congestion, we have certain recommendations here, right? So increase bus frequency, and we can minimize traffic congestion. Again, increase bus frequency, introduce carpools. In this scenario, introduce carpools, encourage biking, and then reduce traffic, encourage biking, right? So based on the traffic congestion, and again, the latitude, longitude coordinates, we have increased uses of buses, carpooling, or biking, right? So there's three alternatives to just one person driving in a car. It can be at least carpooled. You can take a bus or you can take a bike, and depending which part of the city you're in. So this is all for Boulder, Colorado. It can be for any city. Remember, it can be for Phoenix. It can be for San Francisco. It can be for New York City. It can be for Boulder. And based on the long coordinates and the congestion and the intersection, these would be the recommendations that the model is coming up with. Number three, graph neural network, abbreviated GNN for traffic flow prediction. So we can build a GNN model and run that and test that and see what the output of the model is. So here is the data. So I can run this. This isn't actually linked to the Google Maps API, so I can run this in real time. And I promise to go back and fix that error that I saw before I post the code. I will fix that up and get that working for you guys. And then this is, okay, yeah, so we're looking at the same kind of scenario. We have the day, hour, lat, long coordinates, okay, congestion, red light time, and green light time, and we're compiling all of that into a nice packed data frame, and then doing the analysis using a GNN method. In the first scenario, we optimized the traffic flow signals. In the second one, we made the determination it's better to take a bike, to take a carpool, or bus, right? Those are the three options as opposed to just one person driving a car, carpool, bike, or bus. And in this scenario, we're looking again at the hour, the lat long coordinates, and red light, green light times, and making recommendations about which should be used based on the overall congestion of that area, right? And we have the model trained and tested. Again, this is GNN. And the final piece, let me run this one. We come up with predictions. So the model is making predictions right now about how congested a certain intersection is going to be, or a certain area is going to be. Let me run the, I just ran the prediction. Let me print it. And based on Monday at 8 o'clock in the morning, this is the latitude, longitude coordinates, and the red light and the green light timing, right? These are in terms of seconds, right? So red light is on 45 seconds, green light is on 75 seconds, and the predicted congestion at that intersection is 24.59 seconds. So if you're driving through there, sorry guys, you're going to have to wait about 25 seconds. That's how long it's going to take to get through the whole intersection. Okay, so there you go. You have three different types of analysis here to try to understand and predict and manage urban traffic flows. How can we improve it? How can we make it better and reduce this congestion that we all have to deal with, right? Every single one of us can't get away from it. So here I have my notes. GNNs are well suited for traffic flow prediction. We just saw that. For understanding what's the wait time going to be, what's the optimal time to flash the red light, what's the optimal time to flash the green light, right? Depending on the intersection, historical travel patterns, latitude, longitude coordinates, so everything is mapped together and matches excellent. We set up and ran the GNN model. You just saw that. And in my final notes here, I have as a conclusion, simulate different transportation policies. We can test different scenarios. That's what we did. Increase bus lanes, decrease private vehicle volume. Okay, that's what we took a look at too. Introduce tolls. So that's another option. We just got this in New York City. Congestion pricing, right? Where they charge you a lot more money to go through the tunnel, Lincoln Tunnel, and the what was that thing called? Lincoln and I always forget the other one. I can never get that straight. Under the the Holland Tunnel. I guess it's called the Holland. I always forget that thing. Anyway, so the congestion pricing kind of controls the flow of traffic and decreases traffic going through the Holland Tunnel and the Lincoln Tunnel, underneath the Hudson River on the west side of Manhattan, right? So that was just introduced a couple of weeks ago, and that's great. Everybody loves it. No, I'm just kidding. Everybody hates that thing, but that's one way to deal with traffic flow too. Okay, so there's a bunch of ways. Remember, I said before, there's probably at least a dozen different analyses we can do. I looked at 3 here, so 3 different case studies, and I proved 3 different ways to make improvements. So that's what this analysis was about. So that's it. I'm going to wrap it up here. I will go back and fix this issue that we saw before, and I will post the video and the code in just a little while, and I'll see you guys in the next video. Take care. Bye.